Looks like I'm live. Am I? And today is going to be a good session. What do I mean by good? Today we are going to, yep, I'm live. Today we are going to do exercises in assembly. Page number around 300, fraction part. We did that. Yep. Is this on integral mathematics? Yep, floating point. Chapter 9 exercises. That is cool. Yep, here. We in this chapter we learned about FP and neon coprocessors, and FP is a unit which is especially designed to perform floating point mathematics, and neon is a unit which is designed to do single instruction multiple data set, that is vector arithmetic. And what do I mean by that? Vector means a set of data. So using neon instructions, we can do simple arithmetic operations on multiple data points at the same time. That is, we can add, for example, four pairs of number and get four different results for every pair. Like four results total. Adding one pair gives us one result, and adding four pairs will give us four results. And that is it. That is what we learned in this chapter, which was crazy. I didn't knew about that. Now, how many registers does the FP Neon coprocessor add to the AArch64 architecture? Well, there are, first of all, 32 vector pointer registers, floating point registers, which are 128-bit long, and then there are two other registers whose name I forgot here. Yep, yeah, from V0 to V31, we have 31 vector registers, and then we have floating point CR control register and floating point, I guess, stack registers. I do not understand the working of these two completely, but the thing is that here are from V0 to V31, we have 32 128-bit registers, and these two are of a word length that is 32-bit long. So we have in 32 plus 2, 34 extra registers for FP neon instructions. And that was question number one. Then what is the purpose of AHP, DN, and FZ, R mode, and FZ 16 bits in FPCR? Okay, now we need to get into the details. In floating point neon unit of AArch64, what do the floating point control register and floating point stack register, I guess, do? Let's see. In floating point neon advanced SIMD unit of R64, the floating point control register and floating point status, not a stack, status register serves as control and status registers for floating point operations. Floating point control register. Shit, my tongue is not bending. So wow. Tongue is not bending, and thus I am unable to speak properly. Now, the floating point control register is responsible for controlling the behavior of floating point operations. For controlling the behavior of floating point operation, it holds settings related to rounding mode. Yep, yep, that is what we learned. Rounding mode determines how floating point results are rounded. Example, rounded to the nearest towards nearest zero or away from zero, or to the nearest even number, or or to plus infinity or to minus infinity, right? Exception traps controls whether floating point exceptions like division by zero trigger traps. Okay, flush to zero controls whether subnormal denormal numbers are flushed to zero for performance reasons. Default NaN mode forces all NaNs, not a number, to default canonical NaN value. Okay. And half precision control controls special handling of 16-bit FP16 floating point numbers. FPCR fields. Okay, it has been divided into fields from bits 22 and 23 have the R mode, rounding mode. Okay, from bits 22. I don't have to remember the exact number. I have to know that at some point the FPCR register uh, specifies the rounding mode. Okay, it takes 2 bits and 1 bit. FZ specifies flush to zero mode. Okay, and then 1 bit is for DN, default NaN mode. If something is NaN, then if the output of your operation is not a number, then that value will be replaced by the default NaN value, default not a number value. Then I have the bit 27 represents AHP, alternative half precision format. I can specify another format for half precision numbers. Okay, okay. 28 and 31. From 28 till 31, that is 28, 29, 30, 31. 4. So just minus the upper range from the lower and add one. Traps. Exception traps enable bits. Okay. Floating point status register. FPSR. The floating point status register holds the status flags and exception flags for floating point operations. Oh, like status flags like program state. It records whether a floating point operation resulted in conditions like invalid operation, square root of a negative number, division by zero, overflow, underflow, inexact result, precision loss due to rounding, precision lost due to rounding, and then it has the zeroth bit specifies invalid operation. The first division by zero, if it is one, then I have divided by zero. If the second one is one, then the number has overflown. If the third one is one, then the number has underflown. If the fourth one is one, fourth bit is one, then I have rounded down and lost my precision. And if the fifth one is one, then the input was denormal somehow. And these remaining bits, not the remaining from 24 to 31, that is 8 bits represent cumulative exception flags. Okay, you can rewrite these registers using system instructions in assembly. MRS, MRS, these are system instructions. Read F. Okay, these are for reading move register status, FPCR, FPS. Okay, move from this to this. Okay, move this into this and then from move into register from special register and move into special register from normal register. Okay, these registers are crucial for fine-tuning floating point handling exceptions and optimizing performance in ARM64. Okay, there are some things that I do not understand. Floating point control register for rounding mode. Okay, that I get. Exception traps. Okay, what is flush to zero? What is flush to zero? Controls whether subnormal denormal numbers are flushed to zero for performance reasons. What is flush to zero? And what are denormal numbers? Let's see. What is flush to zero? Flush to zero is a mode in floating point arithmetic where very small numbers called denormal or subnormal numbers. Very small numbers are called denormal or subnormal numbers are automatically set to zero instead of being processed normally. And I guess that can increase performance because doing any mathematical operation on a very small number, very small fractional number, is comparatively harder and more expensive than using a zero instead. This is done to improve performance because handling d-normal number is slower on many CPUs. The flush to zero mode is controlled by bit 24 in the FPCR floating point control register. When FZ is 1, any denormal input or result is replaced with 0. When it is 0, then they are handled normally. What are denormal, subnormal numbers? Denormal numbers or subnormal numbers are very small floating point numbers that are too small to be represented with full precision in the IEEE 754 floating point format. Normal versus denormal numbers. In IEEE 754 floating point representation, a normal number has the format this. Yep, the sign bit 0 or 1 multiply by 1 point in the fraction multiply by exponent minus bias. For denormal numbers, the exponent is all zeros. The exponent is all zeros and the leading 1 is the significant and the significand is missing. That is value equals to this and exponent is 0 bias and the leading bit in the significand is 1 is 0. The leading one in the significand is missing, that is this is 0 instead of being 1. This allows for gradual underflow, meaning we can still represent numbers smaller than the smallest normal number. Exponent is 1, denormal exponent is 0, Mantissa starts with 1, Mantissa starts with 0. Here it is like this, and here it is like this. Okay, denormal numbers help prevent sudden loss of precision underflow, but they are slow to compute because CPU must handle them using a special logic. Denormal numbers are used is a way to represent very small numbers. Denormal numbers slow down floating point calculations because they require special handling in hardware. Many processors, including ARM AArch64, provide the flush to zero mode to improve performance. Advantages of flush to zero: faster floating point operations, avoid costly normal number handling. Disadvantages of flush to zero: loss of precision by very small numbers for very small numbers, can use subtle numerical issues, can cause subtle numerical issues in some applications. Example, denormal numbers versus flush to zero, and this is okay. Okay, that makes sense. So now I guess we can do that. AHP in FPCR. Okay, flush to zero 16, flush to zero, and R mode. R mode is rounding mode. Uh, 2 bits, that is bit 22 and 23, I guess, are used to represent the rounding mode, and there are four rounding modes because 2 bits are used to represent them, and 2 bits can only make four patterns, right? And what are the rounding modes available to us? Mhm, mhm, mhm. Yeah, I already forgot. I have already started to forget all of these things, but I do remember all the, I guess, major stuff. And if whenever I am stuck anywhere, I can just backtrack and come back. Flush, fused, multiply, accumulate. Okay, I didn't understand. A fuse multiply accumulation operation does not perform rounding between multiply and add operations. And after reading that, I just moved on, even though I didn't understand that. Yeah, but I can always backtrack and get back here, get back here, or I can always use ChatGPT to understand it when I actually require it, right? Um, what were the rounding modes? Mode, is this it? Um, yep. A. A means away from zero, away from zero. M minus towards minus infinity. N towards even number, and P towards positive number. And Z towards positive infinity. P is towards positive infinity, N is towards even, and Z is towards zero. Okay, those are the rounding modes. And now, yep, rounding mode plus to zero. Plus to zero means that if we have a d-normal, a very small value, subnormal value, then it will be replaced with a zero instead of being a very small value. And fz 16 bits. Maybe we have, I don't know what the heck is fz 16 bits. Fz z 16. Fz plus to zero. Yeah, that is fz 16 plus to zero mode control bit of half precision data processing instructions. Here plus to zero, and here are the rounding modes. 0 means round to nearest, round to plus infinity, round to minus infinity, round towards zero. Okay, those are the four modes, and this is much better. Alternate half precision control bit use, i.e., IEEE half precision format. Use alternate half precision format. Alternate half precision. This bit tells us if we want to use alternate half precision format or the IEEE half precision format. This one for replacing a not a number value with the default not a number value. And this one to flush to zero. Very small numbers are replaced with zero. And R mode, here are four R modes available to us: round to nearest number, round to plus infinity, round to minus infinity, and round to nearest zero. And then we have FZ16, FZ15 is a bike, and plus to zero mode control bit for half precision data processing instructions. Plus to zero mode control bit for half precision data format data processing instructions. This controls flush to zero for half precision data formatting instructions. Disable flush to zero mode for half precision. Okay, this bit controls the flush mode for half precision values. Okay, I guess that makes sense. But why do we have a separate flush to zero for half precision format? In AArch64 we have FZ16 which controls the flush to zero option for a half precision value. Why do we have a separate bit to represent, to specify that? Why won't the general fz bit suffice for this? Let's see. Great observation. Thank you. The fz flush to zero bit and the fz16 flush to zero for floating point 16-bit exist separately in AArch64 because half precision floating point numbers are often used in different contexts compared to single precision or double precision 64 double precision numbers. Here is why ARM architecture includes a separate FZ16-bit independent control for FZ for floating point 16 half precision workloads. Many applications that use half precision, such as machine learning and graphics, because why do machine learning and graphics use half precision? Because machine learning and graphics do not have very large values that they want to add. They have a lot of smaller values that they want to process at the same time. And that is why half precision suffices for their use. Prioritize speed over precision. And some workloads, like general purpose computing, may want to flush floating point 32 and floating point 64 denormals, but keep F floating point 16 denormals for precision. Okay, that makes sense. Some workload might want to flush the higher precision values, but want to, because if a higher precision value is subnormal, then it means that it is actually really small, and it would make more sense to flush them to zero. Then a 16, then a half precision value, because half precision values range is smaller, and thus the subnormal value will be in absolute terms smaller than the subnormal value for 32 and 64-bit half precision values. Other workloads like deep learning interface might want to flush only FP16 to speed up neural network computation while keep the higher bits intact. Having a separate FZ16 allows the system to optimize FP16 handling without affecting single and double precision operations. Okay, that makes sense. Half precision is common in AI graphics in different use cases. Machine learning models like those running on ARM-based AI accelerators often rely on half precision combination. Many GPUs and AI, okay, let's just go with this. Many GPUs and AI accelerators aggressively flush half precision denormals to zero for performance reasons while keeping higher precision float unmodified. Okay. So yeah, and that is just that sometimes we only want to flush or not flush the half precision values, therefore we have a separate bit for it. That makes sense, I guess. So we have FZ16, which specifies if we want to flush the half precision value or not. Then we have two bits which represents R mode, and that is one is to the nearest number. Then we have one mode for rounding off to minus infinity. Then we have one mode to round off to plus infinity. Then we have one mode which rounds off towards zero. Then FZ, this specifies if you want to flush to zero sub or subnormal values in single or double precision values. Then we have DN, do not disturb. What the heck is DN? Wait, we will come to back. Then here we have PA half precision, alternate half precision, which specifies do we want to use the IEEE standard for representing half precision values or an alternate standard. And then what is DN? What the heck is DN? It was somewhere around, you know, DN, default time, of course. Yes, makes sense. Default NAN, which says that if a nan value is outputted by any of the operations, then that nan value will be replaced by the default nan value. Then moving on to question number 3, how are floating point parameters passed to subroutines using registers? How is a pointer to a floating point value of array of values passed to a subroutine? How is a pointer to a floating point value or array of values passed to a subroutine? Just put it in one of the registers. Just put the pointer in one of the registers and point and call the subroutine, branch off to the subroutine. That is it, right? Let's see, passing floating point parameters in AArch64. In AArch64 function arguments including floating point are passed according to the procedure call standard for ARM AArch64. ARM Arch procedure call standard. The key rules for floating point parameters are floating point arguments, single precision or double precision are passed in registers V0 to V7. Yeah, like the same way we do in normal values in general purpose registers. V0 to V7 are used for passing the parameters, and then if there are more parameters than 8, then they are pushed onto the stack, and the return values are also returned in these registers from V0 to V7. Yeah, that is it. Additional floating point arguments beyond 8 are passed on the stack. If a function mixes integers and floating point instruments arguments, then integer arguments go in the X registers and floating point in the V register. For example, this. The first argument A is passed in V0 and B is passed in V1. Then return value is also in V0, passing a pointer to a floating point value on array. Here I take in a pointer to a double. Shit. Here I take in a pointer to a double, and then I go to that pointer, I get that value and add to that pointer 1. Example 1, passing a pointer to a single floating point value. Pointers including pointers to floating point values are passed as normal integer values in x0 to x7. The pointer p is passed in x0. Inside the function, we dereference x0 to access the floating point value. Equivalent AArch64 assembly. I get load the value from a certain register, load double from address in x0 into d0. Yep, because in x0 I have the address, then floating add, I add to it 1.0 to the value stored in d0 and save it into d0. Then I store the value from d0 into the address at x0, and then I return. That is cool. Then passing a pointer to a floating point array, the same thing. I take in a pointer and int, which is total length, and start I equals 0 till I less than n I plus plus total. I keep dereferencing. This is essentially dereferencing with an offset, and add it to the total, and at the end I return the total, and I will get the pointer in the first register x0 and n in the second register x1, like x0 and x1. The return value is stored in v0 because the return value is a floating point value. Thus we will use a vector register to return a floating point value, and since the answer is going to be a double, I will be using d0 to represent, yep, d0, and then I return. That is cool. And now write the following code in AArch64 assembly. For x equals x plus 1, and then inside nothing happens. Oh shit, here it is. um, I will go to the folder where I do my assembly things, and cd book, assembly book, and here I will do chapter 9.s. And in chapter 9 I have, what do I have? I have a variable called x, which keeps incrementing by 0.1 till it gets till 1.10.0. Okay, do I need something in the data section? Yes, I would like to print x, and print x for every increment. That would be cool. So in the data section, I will define two formats. One to print x during every iteration, and one to print x at the end when I have come out of the loop, when I have came. Now, what is going to be the format number one? Format number one is x, x and %d, and then new line. And then format two is finer xo %d, and then that is a new line. Yep. And then in the .text section, I will say that I have a global thing called main, and align it for 2 bytes into 4 bytes. And here I will do what am I going to do? Here I will write, first of all I will store the stack point, store the pair of frame register, frame pointer, not register, and linker register onto the stack by pre-incrementing the stack by 16. And then I would like to initialize. So move F or F move. What is it? Initialize the first zero register. Where I have all the instructions here. Move. Which one is for moving? Move between data registers. Yep. F move. F move into the double zero, the value 0.0. Is that where I have to start x? Yep, 0.0. Okay, after doing that, initializing x, let me get the address for the format string in the zeroth, general purpose zeroth register. For that, I will first get its page address, ADRP, into the zeroth register for fmt1 at the rate page, and then I will add to it the page offset at the rate page off. Now I have that, and then I will define a loop which will first of all f add to the d0th register and store to the d0 register what value, hashtag 0.1, and after that it will check branch. First of all, it will compare the d0 value with 0 with x zr, zeroth register, and branch back if less than. If it becomes equal to, I go, while it is not equal. Okay, so let me do for that. If it is not equal, if the operation is not equal is ne somehow, and if it is not equal, then I will branch back to the loop. And also I would like to goddamn print it. So let me get some storage onto the stack for storing a double. For that, I will get 16 bytes onto the stack. And what will I do after adding? I will do fmove. No, just normally store the value in D0 onto the stack. And after doing that, I know that I have the print. I know that I have what I want. In the zeroth register, I have the address for the format string, and onto the stack, I have the value that I need to go give to the format string. Therefore, I can just call printf here, which will do its work. But then printf can change the contents of x0. Therefore, I will move into, let's say, the ninth register the contents of x0, and the ninth register is no, into the 19th register, which is non-volatile. But before that, I would also have to store the original contents of the 19th register. So store x19 onto the stack with an offset of 8, and yep. And before calling this every time, I will be moving into the 0th register the value, the address for the format string from the 19th register. So then I have the value that I want to print, and also the format string's address in the 0th register. Then I can just call the printf function, then compare and loop back. Yes, now when I get to this point, I will have what I want in the D0 register. So I would like to get the address of page address in the 0th register for the format string 2, and then add to it the page offset. Okay, now I have the address. Wait, at this point, uh, I have the strings address in the 0th register, general purpose 0th x0 register would be much better to say than the general purpose 0th register. So I have the format strings address in the x0th register, and I have the value that is to be given, the second argument for the printf function, at the top of the stack. So I can simply call printf. Now that I have called printf, what do I want? I want to clear the stack, but before clearing the stack, I need to get the original value for the 19th register, which I stored on top of the stack by giving it an offset of 8, that is, and then I can just add to the stack pointer 16, which is just equal to popping the values, and move into the 0th register 0, the value 0, so that I will exit with an exit code of 0, and then load the pair of frame pointer and link register back from the stack, and then give it an offset, add to it 16 post increment, and then just return. Now this should work. Lang let's not count bytes, 1 chapter 9, and the output should go to dot out. Okay, compare D0, and D does not seem to be making any sense for, oh, okay, that the first problems I get totally. You are not wrong there. I have to say dot s keys here. Only then can I do this as keys here, and it seems to be giving me a problem because of this. Clang. Okay, now the only problem is adding a value 0.1 unexpected floating point literal, but I am adding a floating point, so I should cannot give immediate floating point values for add f add. Let me see f add. Where is f add? Here f add. F add. Okay, for f add I have to give registers. I cannot give immediate value. Okay, I feel you. Okay, chapter 9. And what is the other? Okay, for compare I have to use a different compare operation, it seems. Um, Maybe it is f compare, fcmp. Yep, it is fcmp. Chapter 9. And where is the add? Hmm, f add. Yep. Before adding, I will move move to d1. Let's say the value 0.1, and then add here d1 to d0. Okay, first problem solved. And then the compare should be f compare. Now this should work, I guess. Was that a problem now? Didn't I initialize the 0th register the same way, like this? Why is this a problem? I am doing f1 here, and I was also doing f1 here, because expected compatible register or floating point constant. This is a floating point constant, is it not? And invalid operation for instruction. Okay. Let me see. First for f compare, where is, yep, here compare, f compare. F compare will take in a number and an optional something else. What if I want to compare with 0? Right, what do I do then? Conditional compare to 0. Compare to 0. Flags, piece, state, compare E or not E, then update the piece taker. How do I give it 0? I can just put 0 there, I guess. At the compare part, instead of doing this, I can just do this, I guess. At least, shit, error, too few operands for instruction. Okay, so what is the format syntax? I've compared this and this. So do I have to put a 0 into that register and then compare? Okay, let me do even that. Nah, I don't think that is the correct way. How to compare a vector register in AArch64 with 0 and 0 register? How do I get the value of 0? Oh, what the heck is this instruction? Comparing integer vectors with 0. Comparing floating point in AArch64, you can compare a vector register with 0 using the FCMEQ floating point compare equal to 0, or FCMEQ integer compare. How can I compare a double register like D0 or D1 with the value 0? Not a vector register, but only a part of it. I can use it using f compare this with 0. This compares D0 with 0, and that is what I have written here. right? Okay, so point 0, I guess, is an essential part. Yep, that is an essential part. Expected compatible register or floating point constant. This is a floating point constant. This is a floating point constant. Chapter 9. This is floating point constant, is it not? 0, 0.0, 0 0.1. How is that wrong? Um, uh, I am getting error for f move into the D1 register the value 0 0.1. Why is that? That should not happen. There being caused by this immediate does not support arbitrary floating point immediate values in AArch64. The fmove instruction for floating point registers can only take a limited set of representable immediate values and is zero point 0.01 not a thing. The immediate operand immediate. The for fmove must be one of the encodable 8-bit floating point. Okay, and these allow you to encode certain numbers like these, but not arbitrary decimal like this. Okay, solution. Load this using alternate approach. Use a general purpose register and fmove. Since fmove can transfer values from a general purpose register to a floating point register, you can load f1 into a general purpose register and move it. And this is the IEEE representation for a for 0.01. Use LDR from memory. Oh, I can give it as a literal value in the literal pool. This works because the assembler converts this into a memory reference automatically. Then double point one is store point one. That seems much better than storing this value, then storing the IEEE standard value in a general purpose register and then moving that into a double vector register. Just and that is just too much work. This seems much better. So I can call it increment and it will take up double space and it is called the value it stores is 0.1 and here I would like to store this into a general purpose register. Yes, I will have to do a few more things, but let's first do this. Get its address in the first register, let's say, for increase by first getting its page address, then I will add to it the increase page offset. Okay, and then load the value into the 0th register, the the value at the memory location whose address is at the first register. Now what do I want to do? I have the value 01 in a general purpose register. I would like to store it. I would like to store it in a non-volatile general purpose register so that it is not lost during operations. Or I can, instead of loading it here, I can load it directly into D1 here and skip this part. Now that should, I guess, work. That at least compiles and okay, X is stuck at 5 somehow. And X is stuck at 5, 5, 5. Why? I have a dream. Yep. Why is it stuck? Is D1 overwritten at some point. Is that it? And then D1 is not printed anywhere. Let me print instead of D0. Let me print D1, and we can observe that. Okay, yes, D1 becomes 0. That is just sad. How do we fix that? I can store D1, but why would D1 become 0? Because I am calling printf, which could be messing up with D1. Okay, printf is a bitch, it seems like. But, so what I can do is store this value into a non-volatile, into, let's say, first I will get the value in the general purpose register, then I will move it into a non-volatile general purpose register, and then I will keep moving the value from that general purpose register into D1. That is good. Or I can directly add that value without moving it to a vector register. Okay, so we need to get a bit more space here and put 16, an offset of 16 here, and yep, store the contents of store pair of 19th and the x20 register here, and then move the format string address into the 19th register, and then I will move into the 20th register the value from here, and here is a comma is needed. Then instead of doing this, I can do x20. It seems I can do that, right? Yep. And I will keep adding and storing d0 onto the stack, and then I will keep calling printf. Okay, and then compare. Yep. And at this point, I will load the original contents of x19 and x20 back from the stack pointer, and it had an offset of 16. Then I will add to it 32 to pop from the stack, and just this seeing invalid operation for instruction. Okay, so I will have to keep moving this value, f move into d1 from x20, and I will keep adding d1 here. That should not cause a problem, but it did not. And okay, x is very much negative somehow. Chapter 9, why is that? Let me print. I want to see d1 here. Is it not working properly? Well, it is not working properly, but what is the reason? Wait, this is the reason. This is the value that I'm adding to it, but this is not the intended value that I wanted to add. 21. There is a problem here somewhere. Storing. So I guess when I am loading the value from here, loading the value into a general purpose register and then storing it, moving it, when I'm loading the value of double into a general purpose register like x1, and then after loading it into a general purpose register, and by keeping then moving it to a vector register, I guess the format is not matching. Here I'm using d1, that is double bits, which is 64 bits, and I'm using X20, which is also a 64-bit register. So this should not happen, but it is. First of all, why is that happening? And is that is that what is happening? And second of all, how do I fix it? So here I am using X20 as a volatile register. Instead, I can use here get the value in let's say D um in D1, and then I will store the value from D D1 onto the stack, and nope. What is non-volatile vector register? That is D19. Let's just use D19 for our purpose. And here also D19, and here I will get the value from D1, and here instead of moving the value from X20 I will use D90 for that, and keep adding that, and then at the end, instead of getting value into X20 I will get it into D19 and do this. Boom, done. Invalid operation for instruction. So it seems like at one time I can only do one thing. Invalid operation for instruction. How the heck is this invalid? Invalid operation operand for instruction. How can I not move into the D19th register the value from D1? That does not make sense. Okay, first let me split this pair into a single and store them separately one by one, giving this an offset of 8, and store D1 onto the stack with an offset of 16. Yep, and move, and then yep, here also replace this and move them separately, give this an offset of 8, and load register D19 with the value from the stack with an offset of 16, then add 32. And this should work, but this command right here is giving me error. Why? Why? Why is D1 register such a bitch? Why is it invalid? Does D1 refer to something else? What if I use D2 instead of loading a value? Here I can do D2, and here also. Oh, this should be D90, and here also I can do D2. Okay, and F move into D2, and at the end add D2, and here do this. That should do the job. Oh. Okay, I see it. I was being stupid. This is supposed to be F move. And yes, I can use D1 without a problem. D1, D19, yep. F move into D1, and here also D1, and store from D0. Yes, because D0 calculates the sum, and yep, this should work. At least it is compiling. And chapter 9. Okay, let me just directly print the value that I'm getting from the address of ink. Hmm. Here I would like to print the value from D1. How do I do that? For that, I have to get the address of format string 1 into the 0th register. So at this point after this, I have the address of format string 1 on at the 0th register, and after putting the offset, I can store the value in D1 onto at the top of the stack, then call printf and stop all of this. Just discard the loop. Comment it out and clang dot slash out. Chapter 9 D0. Ah, shit. Why is that happening? I am using a double space to store point 0.1. What if I load the value in x1 and then store from x there? Okay, that is also wrong. Why am I not printing it in the correct format? I am using dup. Should I use float? Let's float. Okay, that is correct now. Okay, and I have to use fcompare here. Compare it with 0 like that. Okay, and then keep looping back. Ah, shit, it is supposed to be 1. 10. Ah, shit. Okay, I was wrong. Load in the replace this with D1, and I do not have to print these at the end, and this time it does not work. Expected floating point constant. Why would you expect floating point constant like that? In chapter. Okay, let me store it into a register again. Which register do I store 10 to? The floating point number 10. Let me get some more space onto the stack. 16 plus 16, 48, 48, 48, and let's replace this like this. 16. Give this an offset of 32. Give this an offset of 16, and then store the value at D20 onto the stack with an offset of 8. I don't know. Yep, 8 sounds good. And F move into the D20th register the value 10.0. Yep, that also makes sense. And then here compare with D20, you bitch. And then here I will load also the value of D20 register from the stack with an offset of this. 16 is good here. And here the offset was 32. Then add 48 to pop everything off from the stack, and here we go. And that is wrong. Why? I'm storing D0 onto the stack, and I am printing D0, and I am adding not D1 but add D19 directly. D19 contains the value, right? What does D19 contain? D19 contains the value of D1, which is from here, and yes. So why is X not increasing? Why is X not increasing now? I am doing f add and adding the value in the 19th. Let me print D19 then. Store D19. I will be printing D19. Not slash out. D19 is also one. Chapter 9.s. Okay, and here I am adding f add the contents of this and store them in D0. Why is X not increasing? Why is X not increasing? Even though I am adding here. Why is that 0th register, which stores X, is not increasing? Even though I am adding 0.1 to it. Okay. Let me store D0 and see the clang, and D0 remains at 0.1. Okay, and 25. Let me store D19, which is also 0.1, but when I add 0.1 and 0.1, it seems to give me 0.1. Okay, let me ask this guy. In the D0 register, I have 0.1, and in the D1 register, I have 0.1. Oh, well, at least it is increasing once, right? Because when I do this, I am initializing the D0 register with 0. Yep, D0 yep, here I am initializing the D0 register with 0, and then when I'm printing D0 afterwards, I am getting 0.1. So at least it is getting added once, at least once. But there are other problems at play here, it seems. It is getting added at least once. Okay. Is getting added at least once, but why only once, and why does it stop after that? Even though D19 is still 0.1, can it not represent it in that way? Can this format not? I am adding 0.1 to X every time the C code contains a subtle bug. What is the bug? Ah, shit. Let me ask this guy. In the D0, wait, is this the, what is this? Huh. In the D0 register, I have 0.0, and in D1 register, I have 0.1. Why if move D0 the value 0.0 and ADRP. Let me just copy 23, copy this, Control V, this. Let me tell it that this is the shit. It got lost. I have point 1. Let me tell you that in the dot data section I have this thing, and then in the dot text section I have fmove into d0 value 0.0 0.0 and ADRP get the address of into. I can just copy, that would be much faster. Format string increase, then load the value in d1. But then when I am adding them inside a loop, the d0 register only gets increased to 0.1 and doesn't go further, doesn't increase further on further addition. What did I add? A question mark. Not is not accumulative. Is not accumulative property when adding d1 inside the loop. Here is a possible reason and fixes. Precision floating point. The value point 1 is not exact in binary representation. Continuous accumulation of might not behave as this. So how do I add? F add contents of this and this, and then B go back to the loop. That is what I am doing. F add this and F compare this with 1.0 and then branch loop. If less than, then branch. But that does not work. F add is not working, and here I am doing F add. After moving the contents from the D1 register into the D19th register. Let me write this code in C and see. Increase x vector dot c. Include stdio dot h. Then int main. Here I have double x equals 0.0 and then for I can just do this x equals 0.0 while x less than 10.0 x plus plus that, and remove the initialization from this, and then printf percent x is percent f new line and give it x. Clang increase vector point, send the output to dot out, and okay, it is working here. Now I want to get the assembly code. For that I do slash this and increase vector. S is obsolete, so capital S. Okay, that is not obsolete. And capital S, and send the output to increase x vector dot s and increase s vector dot s. Here is the assembly code for that. Okay, here I am getting 48 bits, and am I storing anything in the data section? Yes, I am storing just this but not in the dot data section, in this only. And then where am I? Or yep, here I am moving 0 to D0. Okay, and then storing the value in that in a stack due to some reason, and then I am branching to BLL01, which is just right here, this inner loop header. There are also comments by the compiler. Compiler is good, it seems. And then I am loading the value from there into here, and then I am moving 10.0 multiple zeros into D1. And then I'm comparing X1 with temp and conditionally select PL into W8. Okay, conditionally set PL from W8. What is PL? What is PL? Oh, PL is the condition, and PL is some condition. Okay, and then I'm doing TBNZ and branching to this, and from here I'm branching to this directly, and from here I'm doing load the value in DS and F move 1.0 to D1, and then F add, I'm adding 0.1 to it. No, I want to add not 0.1 but increase vector.c. Yep, I don't want to add 0.1, I want to add plus equal 0.1. Let's see how that works. And increase vector.s. Yep, now the code is much bigger. Let's see. Yeah, this is the offset for this. Okay, so I guess I will have to use this quad in chapter 9.s. So instead of this, seems like I have to use this, and here quad clang chapter 9 into dot out dot slash out, and nope, S funktioniert nicht. I am moving 0 into D. Let me do this. Let me go. I don't think ChatGPT will be able to answer this. This loop is getting stuck at D0. Shit. Okay, I guess I see the problem. So the thing is that since I am using D0, for the sum, which is a volatile register, and after that I'm using printf to get to the answer, I am messing up because printf can change the volatile register. Therefore, I need to use a non-volatile register for my purposes. So I will store the value of, say, D, store the value of D21 onto the stack with an offset of 32. What comes after 32? Well, I can, yes, 32 is good. Here I can give an offset of 24, and then here 16, and then here 8. That is good. Now instead of initializing this to 0, I don't have to initialize this. I have to initialize f move d1, no, d21, the value 0.0. That is good. And here instead of D0, I will be using 21, and here also I will be using 21. Okay, and then here I will be using register 21. Yep, and here 21. Yep, and yeah, that no. Since I have changed up my usage of stack, I have to make some changes here also. Load into the D21 register value on from the stack with an offset of this, and do 16 here and do 24 here. Is that Does that match the above things? Yep. And now lang it and run it, and it does not work. Okay, it goes very fast, the thing. So instead of not equal to, I should use greater than. In chapter 9, when I am comparing the condition here and then not equal to, I should use greater than. If the contents of 21 go greater than 20, no, not greater than, but if they go loop only if they loop only if the contents of the 21 register are less than or equal to the other one, and it works. And I should skip the less equal to part. I do not want them to be equal to loop after that, and they have become equal. So less than, not uh, uh, less than, only loop when it is less than. Okay, D1 contains 10.10. D21 contains 10 point, let's say 10 at one point. So after getting, after making it 10, 10, 10. Oh, let me do, this is not an exact representation of it. Hmm, 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 hmm. Ah, I see. Let's make it 10.1 so that we do get the correct answer. 10.1 is one of those values which cannot be represented fully. Shit. So I will have to make do with that. Or yeah, I will have to make do with that. Yeah. Now, in the previous question, there is a bug. Yep, there is a bug because here we are adding 0.1, which is 0.1, which is in binary not exactly equal to 0.1. Okay, in binary we have 0.1, 0, 0, 0, 0, 0, 0, and some 1 at the end. So it is what we are actually adding is greater than 0.1. Therefore, if we do this in assembly and we compare it with this summing, adding 0.1 and a little greater than that value to x, which starts at 0, will never be equal to 10.0 because 10.0 can be exactly represented in binary, but zero point 0.1 is not. Therefore, I am not adding 0.1 to this x, I am incrementing it by a little bit by a value which is a little bit greater than point 0.1, and that is the bug. So two ways to fix the code in Arch assembly. Hint: one way is to change the amount of increment, okay, which will change the number of times that loop executes. Well, it is not, I guess, n divided by 0 increase vector. See, well, oh, I'm doing less than, but I should do not equal to and line increase dot c to the output dot out, and then run it. Let's see what is the problem is. Yeah, that is the thing, right? The loop keeps going on if I'm doing not equal to. Yeah, the same problem exists in C. So two ways to fix the code in AArch64 assembly. Int One way is to change the amount of increment, which will change the number of times that the loop executes. Okay, I can do that. Here I can change the amount I am incrementing to something that can be better represented in C. I guess this should be correct. /out. If it is not, what are the values that I can perfectly represent in binary? What are the floating point values that I can completely represent in binary? 0.5, it seems. Yeah, okay. No, I can change the increment to 5 ./out. How it works. So that is one solution, because 0.5 can be exactly represented in binary. Therefore, when I am adding 0.5 to x, I am exactly adding 0.5, nothing else. That is good. Yeah, of course, 0.5 can be added to binary. In binary, 0.1 is 0.5. Yep, I can exactly represent it. But now so another way to do this. Well, another way is to replace this by less than sign. That would also fix it. That is the way we were doing it first before. Now the fixed point, how much time has it been? 1 hour and 28 minutes. That is a lot of time. We got stuck in questions and we have only done 5 questions. Let's move. Let's see if we can complete all of these. The fixed point sign function from the previous chapter was not compared directly to the hand-coded VFP implementation. Based on the information in table 9.2 and table 8.4, would you expect the fixed point sign function from the previous chapter to beat the hand-coded assembly VFP sign function in this chapter? Why or why not? Well, I did not read the implementation of both of these functions. Table 9.2, this is table 9.2, single precision. Well, based on this, what do I think? I would have to see what are the things that I am using and that they are using in, yeah, okay, table 8.4. Where is table 8.4? Table 9.4 tells me that when I'm using single or double precision, then the results of hand-coded assembly are much faster. And based on this, performance of sign function with various implementations, if I'm using 32-bit fixed point assembly language, then it is faster. Okay, and when floating point single and double are generally equal, and when using floating point C, single and double don't make a big difference. Well, but so yeah, I think I will see some increment from 10. It will reach up to 5 seconds, down to 5 seconds, I suppose, and that would be good. So yep, speed increases because wait, let's see, but the increase in speed here when using assembly with a 32-bit value, that is single precision, the speed is about 5. And if I were to use vector floating point for single precision, the speed increases from 5 to, yeah, according to that table that we were looking at, table number this. So single precision scalar, the speed is this when I'm using vector floating point, and for normal C code, okay, for normal C code, the single precision time that it takes for single precision calculation, the time is about this. And when using single precision scalar assembly language, the time decreases to this. So I guess, yeah, the speed will increase because of these stats. Now moving on to the next question. 9.7. 3D objects are often stored as an array of points. As an array of points. Okay, as an array of points where each point is a vector array consisting of 4 values x, y, z, and the constant 1.0, and 3 values these and a constant 1.0. Okay, rotation, translation, scaling, and other operations are accomplished by multiplying each point by a 4 by 4 transformation matrix. The following C code shows the data types and transformation. Write the equivalent assembly code. Okay. Here I have these a point and a matrix. Point is a array of 4 floats, and matrix is a 4 by 4 array of floats. And then X form, not transform, but X form, takes in a pointer to a matrix and a pointer to a point. Okay. Okay, and then I can do ij integer ij point, and I am initializing a point which is a result. Okay, point is an array of floats, matrix is a 2D array of floats. For point, for I from I equals 0 till 4, that is, I will be going through the first row of the matrix, and every column, every place in the matrix represents 4. How do I store? Shit. To store, okay, to store a 4 by 2D array. In actuality, in memory, it will be represented as a linear array where each element is of size point. So moving to the next row would be equivalent to skipping up 4 points, 4 point spaces. And yeah, the total space it will take is 4 into 4, 16 points. Okay, result I equals 0, 0. Okay, and for j equals 0 till j equals less than 4, I am doing I am multiplying that point. Oh, this is I'm multiplying that point with the matrix. And then I'm getting the sum. The j is changing. Okay, I have a single point, and then I have so to simplify what I suppose is happening. Delete raw. Let's say our point is single, just a number, Then we have a matrix 4 by 4 matrix which has some values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Then we have a point, let's say 67. Could have increased it by 2, but okay. And then for result I equals j, I am multiplying it. The point is an array of floats. I'm not storing. So every location in matrix is not equal to a point. Okay. So our point is not this. Our point is somewhat like this. 67, 68. Now we will get our number 69 and 70. And then and then let's say the answer is here. We initialize it with 0 like that, and we start it at 0 and keep adding to it what the ith element from here, no, the jth element. Then I go ji, j is the first one. Okay, when I'm so the answer for this would be multiply these numbers with these numbers and move. The way we are moving is j I, and j is increasing, and j represents the row or the column. I is not changing. And how do we multiply two matrix like that? I am being stupid. What is matrix multiplication? Matrix, how do I multiply a matrix by a vector? Of course, it is not like this. It is matrix multiplication is not like this. It is like this. I multiply these with these and add them, and the sum goes into the first row. So here j represents this number, these rows starting with 0, 1, 2 till 3, and I remains same, and I represents this part. So this is 0i, 1i, 2i, and 3 i's. I have 3 i's. That is how it goes, and to that this is 0, 1, 2, 3, and it is stored in a float. And then at the end, after doing all of that, I do for I equals 0 till 4. I do pi, go to the ith location and store the result onto that. Okay. Okay. I guess we got this. And in chapter 9.s, let me first comment all of this out, go to the top, make some space, store this, yep, 23, 23, this, this will be like this, and yep, this will also be shit, tab, tab. This is okay like that. This is also okay like that. Or, nope, this is not. Is it? For I less than 4. What do that? Okay, so this one is for this, and for this is like this. Only this is like this, and then this is like this, and then this is like this, more like this, and this is like this, and then this is like this, this is like this, this is like this, this is like this, and this is like this, and this is like this. What the heck? And then I will just comment all of this out and won't even look at it, even after going through the trouble of doing it, making it like this. Okay, now the data section. At the end, I would like to print my matrix, but we will look into that afterwards, after we have completed the implementation. For the implementation, I will get some point, not like that, a point like that, which will store float. A float takes a word, long number, and let's say at the start the number is 2, the vector is this, and then a matrix which also stores a word. And now here is the choice. I will make it so that the first 4 spaces, the first 4 words represent the first row, the second 4 words represent the second row, the third 4 words represent the third row. Okay. Yes, that makes sense. Does it? Yep, it does. So what is going to be my matrix? 5, 9, 10, 100, 2, this number, and this. I have 2 rows now, 3 rows, 4 rows. Okay, that should work. And then in the text section, I will declare global main, and let me go a little faster. Main, here I will store the pair tp, the stack frame pointer, and the linker register onto the stack with an offset pre-increment of -16. Then I would like to get the addresses of those things. ADRP, get the page address, and the 0th register for point, and then add to the 0th register offset for page offset for point. That is good. I have the address in 0th register. Then I will get the address in the first register for the matrix, and and matrix hash page to get its page address, and then I will add the page offset to it to get the address for the matrix. Okay, now I have that. Now I need to create a function label called xform, which multiplies all of these and does its work. But where will I store the temporary results? I will not be storing it onto the stack here, and that I can store it on the stack if I want, but no, I won't be. Let me store stuff in the registers themselves. In the yes, I can store stuff in W parts of the registers, or can I load all of these values at once? You wrote in the pre-section, use vector mode if possible. Okay, that is the next question. So right now I have to use normal general purpose registers for this. I have the addresses. Now xform function has the addresses in the 0th and the 1st register. First, yes, I will load the values. LDR load pair into the, let's say, W third and W fourth register. The address is here, and then LDP load pair into the 5th and the 6th register. The address is x0 with an offset of 8 plus 8, 6. Add to it or subtract? Yeah, 16 bytes. That seems like a good offset. Okay, and so now I have the values from the original point, and then I would like to, shit. I will use registers. Okay, move into register W8 0 and move into W9 0 and move into W10 0 and move into W11 0. Okay, now I have initialized my this part. I have the code above here. Uh, so now I have initialized now I have initialized this result part. Okay, this thing. Now I would also need pointers in the counters. So for that, I will be using 12th register. I'm using a lot of registers. W13 to get 0 in the W13th register. Now loop outer loop. It will be posted and at the end of this loop I will be checking compare W12 contents W12 contents with 4 and branch if less than 4 to outer loop. Yep. And also W12, I was going to do W12 plus plus plus, add to W12 1. Okay, and inside that loop I will have this reinitialize these registers, that is this whole part, because I will have leftover values from the last loop, and then after that I need to start another loop. Okay, which is going to be inner loop. Inner loop will be at the end. Inner loop will increment the 13th register contents with 1 and compare those with 4, and if it is less than, then it will branch to inner loop. And what is the thing that I need to do in the inner loop? Inside the inner loop, I need to load the values from the matrix, multiply and store them in the result registers. Okay, so to get the value for this one, this little number, I will run it in a loop once. I will run in a loop 4 times. To get the value for this, I will run in a loop 4 times again. To get the value for this, I will run in a loop 4 times again. For this, I will run it again. Is that how it is going to be? So I do not have to do this inside the outer loop when I have already done this here. Yep. What do I have to do here? Here, I can use a stack for my thing. Instead of using these registers from W8 to W12. Yep. And yep, I can use a stack instead of this. W8 to W8, 9, 10, 11. And so let me get some space in the stack. 64 bytes. Let's just do that. 64 bytes on the stack, which is a lot of space. And in the inner loop, okay, this will be hard to explain because I do not understand this completely, or no, I do understand this, but I'm trying to think about how can I do this. Then I need to get 4 values from the matrix. Okay, I will get them in the at the outer loop. Okay, I have the address, base address in the first register for the matrix. Yep. So store or load xw8 with the value from x1. Now I need to calculate the offset. What is going to be the offset? If w12 is 0, then the offset is 0. The offset is going to be w12 plus 8. W12 W12, can I do this? L logically shift left twice. I don't think I can do this. That would be asking too much. And I will be loading them in pair. Load in pair value into this and W9 from this. If and also into W10 and W11 at the same time with the base address this and 12 with logically with that. Okay, let me use another register to store the offset. To store the offset. So this to offset would be multiply. I will store the offset in the 14th register, a lot of registers. I will multiply the contents of the 12th register with how much? With the size of a point. And what is the size of a point? Point stores four 32-bit values, and one 32-bit is stored in 4 bytes. So 4 into 4, 16. I will multiply this by 16. So for W12 equals 0, I will get 0. For W12 equals 1, I will get 16, and so on and so forth. Fourth, make this. I will be getting value one at a time, and the offset is the contents of this register. Then I will add to W14 4 to get to the next byte, and then load again, and then load again like this into this time the 9th register. Yeah, yeah, yep, yep. And then do this a couple more times. Now load into the 10th register by adding, yep, 4. I have to add 4 every time, and then load into the 10th 11th register. Okay, this much code should get me the values of the matrix in the current code. But then why do I have to go through the inner loop? I can skip the inner loop and just multiply them directly. Right? At this point, I have the values that I want. Shit. At this point, I have the values of the matrix, and now I need to multiply and store them over in the stack. Yes, I will store them in the stack. But before storing them in the stack, I need to store them in a register. So I will be needing some registers to work with. So I have to initialize some registers to 0. What are these registers? 8 to 11 are gone here, 12 is here, 14th has been taken here, but then I cannot use other registers because those are non-volatile. So if I want to store those registers, I will have to store their value onto the stack and then get them back from the stack. Which is just crazy. Let me reduce the number of registers I'm using. Register 0 for this, first for this, third, fourth, fifth, sixth for getting the value of the point. Okay, then where am I using the 7th register? Okay, I'm not using the 7th register, so let's change this to 7, this to 8, this to 9, and this to 10th. And then where is the 11th register being used? Nowhere. I can replace this with 11 and replace this with 11, 11, and yeah, that was it. And here replace this with 11, this with 11, and also this. Okay, where was I using the 12th register? I was using it there. Now 13th, nope, and nowhere. I'm not using 13th anywhere. I'm using 14th here, so I can replace this with 11th. Nope, replace this with 12th. Why am I doing this? To get some space so that don't have to store the non-volatile registers onto the stack to use them. Okay, now how many registers do I have? 12, 13, 14, 15, 16. That is exactly how much I need. And 16th register is also volatile, so that I can use it. I can use the 16th register. So yep, the first sum is going to go in the 13th register, and not the sum. What do I have to do in the 13th register? W13, the first 32 bits of the 13th register, I have to uh, multiply the value of the point. Yes, point. Yes, point. Multiply the value of the point with the corresponding value in the matrix. So what I did here was wrong. Shit. What I did here was wrong because here this gave me the values in the matrix for the current row, but I do need the values in the current column. So I can, how do I do that? So this will, I have to multiply this by 4. 4? Yep, 4. Multiply the current index by 4, and then I will have to add to it not 4, but I have to skip a whole point, and a whole point is 4 into 4, 16. So I will just add 16. I hope it fucking works. I hope it fucking works. Yep, now I have the values for the row, and then I will, so I have to multiply. So first I will move into the, no, I will multiply and store into the 13th register the multiplication of W3 and W7, and then I will add, multiply, and then store. I have to multiply and save the result somewhere, and then add that value at some place. I can do multiply and add, MAAD, MADD. How do I, what is the format for that? AArch64 MAAD instruction, MADD instruction. What is the format for that? What is the time? Oh, it has been 2 hours, but let's see, you got this. Okay, destination register, multiply these, and then add this. Okay, so MADD, store it in the 13th register, multiply the value of the W4 and W8 and add W13, and do that again with W5 and with W9 and add W13, and then do it again, MADD in the 13th register, W6 and W10, and add. So now I have what I want in W13. I'm manually doing it. Shit. The way that I have been doing this will not work. I will have to eliminate the outer loop and write the code manually. That is just crazy. So instead of doing multiply this, nope, I will move into the 12th register the value 0, then keep adding that, and then copy all of this, god damn it, and do this, not 0 but this time add 4, do 4 and get the values, and then multiply and get the sum in the next registers. 14 register 15, 14 14 14 14, and copy this again. Now this becomes 8, same, everything is same here, and 4 becomes, replace this with 5, replace this with 5, replace this with 5, replace this with 5, and after this 8 becomes not 16 but 12, and I hope this goddamn works after being embarrassed like this and replacing a loop with manual labor. 16, yep, I got into the 13, 14, 15, 16th register, and then at the end I want to store these values into the point. And how did I got them from the point? I got them from the point this way. This way, and then I will store them. Replace this with the store pair, not this and this, but starting at register 16, 15, 13. So 13 register 13, and here register, make this 14, and then here register not 14 but 15, and make this 16, and then store them appropriately. What else? Yes, I've got what I wanted. Now I would like to print and see what I got. The dot data section format dot s keys, and here I will print something like this. The values, right? %d, then a comma, %d, then a comma, %d, then a comma, %d, and then a new line. Yep. And then I would like to print these values, but did I mess up with the stack? Yep, I messed up here. This will be good. 11, I'm not using the 11th register anymore. Yep, after storing them in their memory locations, I can store these onto the stack. Yay. Subtract from the stack some location, let's say 32, but 48 would be nice, and then store pair w13 and w14, those are the first numbers, right? Yep, onto the stack, and then store pair w15 and w16 onto the stack with an offset of 6, with an offset of, I messed up, didn't I? Here the offset has to be 8. Yep, the offset has to be 8, and above here also the offset has to be 8 here. Okay, now that is done. Remove the comma. Now I have the things in the stack, pointer, and the onto this stack. Now I want the address for the format string and the zeroth address, ADRP 0 FMT. I will get its page address and then add to it its page offset, and then simply branch the printf function. This might be very stupid, but I hope can I hope no, and then adding to the stack pointer that is popping off all the set that I have put there, and load pair the frame pointer and the link register from the stack, and then return with an exit value of 0, of course. I think this will not work. How can it? Of course. Multiple errors. Invalid operand for instruction add. Okay, first one I get. What the heck is happening here? Oh, 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 uh, okay. All that also makes sense. First, let's fix the error here. Add 0 and this. Let me ask ChatGPT how to give an offset that I want. Here, how to in a str instruction I want to give a base address from another register, and the offset for that address is also stored in another register. How do I give an offset from another register? How do I give an offset from another register? In AArch64 assembly, when using str store instruction, you can specify the offset like this. How do I give an offset from another register? Logically left shift. Nah, that is not what I want. Means store this at. Okay. Oh, okay. So do I have to use, instead of W, do I have to use X, the whole register? The whole register. Let's see. I've gotten a lot of errors. This time the errors seem to be, first error is at 57. Ah, that seems to solve the problem. Okay, here instead of W12, I will be using. Oh wait, I can replace all W12 with with X12. Let me ask ChatGPT how to replace X in Vim. I don't understand. I don't know how to. Then okay, using a command. Yes, this and this. S W12 with X12 and enter. That is Vim. Oh, global. I also have to add globe. Yep. X, replace W12 with X12 globally. Okay, let me move a lot of W12s in a single frame and let's see the Vim magic. Replace W12 with X12 globally and I do not see the magic. Ah, there it goes. There it goes. It happened. It did not work globally. Yes. Hmm. Yes. Replace W12. Oh, does it only see S W12 with X12 globally? Pattern not found, but you found them here, right? Replace W12 with X12 globally. I still have W12. What is that? Let's replace all occurrences in a same line. Okay. In the entire file, I do %s. Okay. Percent is W12 with X12. That is crazy. I can see the change in real time globally. Yeah, that is everywhere in every line. Lang it. I see some values, but then I see segmentation fault after printing. That is crazy thing to happen. So I went here, printed. That is pretty good. And then I messed up somewhere. Why? Segmentation fault. Segmentation. Segmentation fault. Why? Here I added 48 to the stack. And what did I added to the I never did I never subtracted? Yep, I subtracted 48 from the stack. SP, SP. Where am I using stack pointer before? Okay, here and then here. So stack pointer should not give me any error. I subtract from the stack pointer, I use it for my evil purposes, then I add back to the stack pointer and then load from the stack. Oh, okay. Give it an offset of 16. Dot slash out. So if I change these values, none of them was negative, which means that some of the numbers got really big. That is why it overflowed like this. So I should not see any negative number now, but I do see negative numbers, and do I see the same result? Nope, I do not. And chapter 9, is it because 10 seems to be a really big number? Okay, if I do 2 here and 2 here, I should see the same values in the first and the last column. And do I see the same values in the first and the last column? Nope. Actually, I see the same numbers from before, which the result is changing. The third number is changing, which means that I am not inputting from the correct place. I replace this with one, this with one, and replace this with one, replace this with one, remove this, one, remove this, replace with 1, replace with 1, remove, replace with 1, remove, 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 replace with 1, remove, 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 replace with 1. This also replace with 1. That's out. Yeah. The first one seems to be working correctly. The second number is messing up. Second value is messing up. I think the offset here is not working good enough. Why am I adding 16? Okay. In the first register, I have the address for the base of the matrix. Okay, so I will get the first element here, right? And then I will add 16 to it, which will give me the fourth element. Wait. Yes, this will be at 0th address. Then let me create some space to know the ends of rows 3, 4. Yep, these are the rows. So yeah, this one will be at address 0. This will be at address 4. This will be at 8. This will be at 12. Now to 0, when I add 16, I get 16, and 16 holds this. Okay, then I add 16 again. That will give me 32, and this thing is at 20. This is at 24. This is at 28, and this is at 32. That is good. So for the first loop or this embarrassment thing, I get the correct things, and then I should keep getting the correct values. I am moving 4 to 12 and then adding. Is this messing up? Is this uh, here the base address is in x1 and the value in x12 is it being added to the base address. Yes, in the instruction this is being added to the base, contains the offset. The effective address is this 32 bits. Let me do this very manually. Okay, and here I will not provide any offset. Instead of using the 12th register, I will provide the offset manually. Then go to 16, then go to 16 plus 16, 30, 32, right? Yep. And then go to 16 plus 16, 32, 48, 48 place. Yes, then multiply and do stuff, and here start with the fourth with an offset of 4, then 4 plus 16, 20, and remove this, and here 20 plus 16 36. Yes, and remove this, and 16 plus 32 36 46 52 52 52. Yes, and I multiply, and here I will start with 8. Yep, with an offset of 8. 8 plus 16 is 24. Yes, 8 plus 16 is 24. Seems like. And now it is 40 when I add 16 to it, and 40 plus 16 is 56. Okay, and here I will start with hash 12, and 12 plus 16, 28. Yep, and Here I will have 28 plus 16, 34, 44, 44, the offset will be 44, and here 44 plus this, 60. Now, if even this does not work, this manual label. Oh, okay. Let me just fix all this. Das funktioniert nicht. Loading pair here. This is correct, right? At least this much is correct. What do I know at this point? Loading. At this point, I know that getting the values from the matrix is at least correct, and getting the values from the point, that also seems to be correct. Well, let me get these values not in a pair but like this individually. LDR register 4 with this and offset of 4. Yep. And this also LDR with an offset of 8. Yes. And LDR register 6, load register 6, and then from 0 as the base and 12 offset clang. And so what I think the error is that I am accessing some place in memory which I should not be accessing, or maybe everything is correct, but the problem is with printf storing pair. This might be fucking it. Store this store this with an offset of this. How does it go from there? It will store up, it will store up, it will store up, it will store up, it will store up. So if I keep storing from here and add, yes. So I think this store the contents of this with an offset of 4, and then store the contents of the 15th register with an offset of 8. Yes. Then store the contents of the 16th register with an offset of 12. Let me reverse the order of storing them onto the stack, because at one point this was the problem at some place in some code, but not here. Shit. Okay, I will get back to this program, I guess, tomorrow. Okay, tomorrow we will get here, and today it has been a long stream. Shit, I cannot understand what the heck is happening with this function. Am I getting the correct values? Okay, the next steps that I am thinking of is to print the point that I'm getting, and then to print the matrix values that I'm getting. Word is 32-bit. 32-bit means 4 bytes, and I am providing proper offset according to 4 bytes. Okay. How to store 32-bit value from a W register onto the stack with str. It is not str and some variant of str. Nope. Nah, nope. That is correct. The way that I'm storing and loading, that is absolutely correct. The problem is not with that. The way I'm loading and storing values, everything seems to be correct. Let me do 2 here, 3 here, 4 here, 5 here, because those store the values of the points. Okay, even the value. Okay, we'll get to this tomorrow. Okay, and here the stream ends.